Let me highlight just a few concepts for you in the sections 5.1 and 5.2 in Math 1413. A very important concept is to know what these types of numbers are. Many people think they know, but there's little bits of the definition they sometimes miss. So let's go over the definitions slowly. Natural numbers are also called the counting numbers. It's just a different name. So in upper level math, we usually call them natural numbers, never counting numbers. But they're 1, 2, 3, 4, on and on and on to infinity. Those are natural numbers. Whole numbers, like they sound, are whole. They're not fractions, they're not decimals. So it sounds a lot like natural numbers, but we include 0. So if you include 0, 1, 2, 3, 4, 5, on and on and on to infinity, those are whole numbers. So what type of number is 5? It's natural and it's a whole number. But 0 would only be a whole number. What are integers? Integers are all these whole numbers and their negative counterparts. So 0, 1, 2, 3, 4, 5, on and on and on, and -1, -2, -3, -4, on and on to negative infinity. So now we've talked about 3 categories of numbers, and we haven't even included fractions yet. That's what rational numbers are. The root word is ratio. If you can make a number into a ratio, it's a rational number. 3/7, that's rational. 7/9, rational. 13/10, that's improper, bigger on top than the bottom. Still a ratio, still rational. How about 4? Still rational. I can make it into a rational number. So all the whole numbers, all the integers, even the negative ones, they are rational numbers. How about square root of 25? It equals 5. I can make that into a ratio, so it's a rational number. It's sounding like everything's a rational number. How about 4.2? Can decimals be rational? Let's see, can we write it as a ratio? 4 and 2/10. I could multiply 4 times 10, 40, plus 2, that's 42/10. Yep, that's a ratio. 4 and 2/10 is a rational number. But there are irrationals. There's even an infinite number of irrational numbers. Irrational means can't be made into a ratio, not rational. Square root of 3, for example, equals about 1.7, but it goes on and on, 1.732, on and on and on. So it's not rational. It cannot be made into a ratio. So any of the square roots that aren't perfect squares will be irrational numbers. Pi is an irrational number. So there's a whole infinite group of things that are irrational numbers. Real numbers, very quick definition, is all the rational and all the irrational put together. Real numbers are all the ratios and all the not ratios put together. Those are real numbers. Let's use a Venn diagram to make sure we understand that. In this Venn diagram, I've made categories of numbers. The overarching category, the entire diagram, is real numbers. Everything I write on this page better be a real number. What if I wanted to write a 4 on this page? Where would I put it? Is 4 irrational? No, so it can't go in this container. Is 4 rational? Yes, 4/1. But I'm not putting it in this container because it's also an integer. Is 4 a whole number? Yes, then I better put it in this even inner container. But 4 is a natural number, so I have to put it in the innermost container. All the natural numbers are involved in the whole numbers. What's the only whole number that doesn't belong in the natural category? That's right, it's 0. So any other natural number will get put in the natural category, which makes it also within the whole number category because it's a category within a category, a subset. What numbers could go out here? They're not whole numbers, but they are integers. So they're not positive numbers, but they're integers. So the negative whole numbers go out here. What could go in this category? It can't be integers because they'd be within their integer container. So it must be numbers that are ratios, but not integers, not whole numbers and their negative counterparts. So maybe 4.1, which is 4 1/10, which can also be written 4 times 10 plus 1, 41/10. So 4.1 is in this container. Negatives are in this container if they're ratios. Square roots are in this container only if they're ratios, only if they can be made into a ratio like 6/1. What's that leave for this container? All the other real numbers, and there's an infinite amount of them. For example, square roots that aren't quite perfect squares, even negatives. The next category to talk about is absolute value. Absolute value is the distance from 0. How far is -4 from 0? Let's go. 1, 2, 3, 4. It's 4 spaces away. Doesn't matter if you go backwards or forwards, it's 4 spaces away. So if I wrote absolute value, that's what the bars mean, of 4, it's also 4 spaces away. That's why some teachers will tell you absolute value is just taking the sign away. But I want you to know the real definition. It's the distance from 0, which is always a positive number. How far is 14 away? These bars mean absolute value. It's 14 spaces away. How far is -1 from 0? 1 space away. Even though we went backwards, it was 1 space we went. How far is -11 plus 4 from 0? Well, you must work what's inside the absolute value bars first. It's -7. And -7 is 7 spaces away from 0. Next, we'll look at adding with colored counters. This is a great way to show young students how to count with negative numbers. We'll let all the positive numbers be blue, so 8 counters are in this circle. We'll let the negative numbers be red, so there's 3 red numbers, -3, -3. So we teach our students that a positive and a negative counteract each other. A positive and a negative counteract each other. A positive and a negative cancel each other out. And we can see that there's 5 blue circles left. 5 is the answer to 8 plus -3. It's also the answer to -3 plus 8. What property is that? What allows me to take these two numbers, change their order, and still get the same answer? You're right, it's the commutative property. Let's practice adding integers, and remember, integers can be negative or they can be positive. Well, we know 7 plus 11. But what if there's a -6, like on a number line? And what if I want to go even further back, 5 more? Where did I land? I went backwards 6, and then 5 more. That's 6 plus 5. I landed at negative 11. What if I'm up here at positive 7 on the number line and want to go backwards 3? 1, 2, 3. Where did I land? 7 minus 3, I landed at 4. So we need to train our students that minus 3 is the same as subtracting 3. What if we're at 4 and we want to subtract 9? We're up here at 4, but we want to go backwards 9. Where will we land if we go backwards 4? We'll be at 0. And then we want to go 5 more for a total of 9. We'll be at negative 5. Both of these numbers, one is negative, one is positive. One is negative, one is positive. So we're actually subtracting 9 minus 4. And we keep the sign of the bigger number. We did that here too. We subtracted and we kept the sign, 7 was positive, of the bigger number. If you have a number and you subtract that number from itself, you land with 0. You've canceled out the numbers. We need to remember our properties as they apply to integers. Associative property is who you associate with. You can take n plus r and then later add another number, or you could have added m plus n and then later add the r. That's the associative property. You'll get the same answer. Closure property, remember, is when you have a number plus a number and the answer is also in the same category. An integer plus an integer will always be an integer, so that's the closure property. Commutative property, do you remember what the rule is with that O? The order matters. If I have 2 plus negative 3, it better equal negative 3 plus 2. And it does. That's told to us by the commutative property. This might be a new one, additive identity property of 0. What happens when we add 0 to any number? Let's try. We keep that number. Even if it was negative, if we add 0, we retain that number. We retain the identity of the number. That rule is called the additive identity property of 0. I've already shown you examples of adding with a number line. We've talked about subtraction, but let's go through some of the more unique ones, like this one. If you have minus and a minus right next to each other, they turn positive because minusing a negative means what's the opposite of a negative? It means you were headed backwards, but then you turned around and went the other way, forwards on the number line. So it's a positive. Two negatives immediately following each other. Not here, there's a number in between, but immediately following each other turn to a positive. Right here we have two negative numbers immediately following each other. They'll turn to a positive. So now we have negative 3, positive 10. Are the signs the same? No, one's negative, one's positive. So we subtract, and we must decide what sign to keep. We keep the sign of the bigger number. 10 was bigger and he's positive, so our answer is positive. Here's the rule we learned on this page. A negative and a negative is positive. The last thing I want to talk about is magic square. I think I'll do it in another video.